So, before starting, just you remind that if you want at any moment to join the organizing committee of the What Is seminar, you are invited to. Then the second thing is that next Friday there will be a What Is seminar. So what is a condition number by Paul Brady, up to you. So more information will be sent next Monday, but you are also invited to go to there. Okay. Now we start with this. So what is PPP, RP, and the probabilistic complexity classes? So essentially, if you look at which are the classical complexity classes which encode probabilistic computation, are essentially this PPP, RP, co-RP, ZPP. This P is the usual class P of P versus NP, so this is what you can solve in the deterministic polynomial time and efficient way. And now I'm going to explain what is these four classes over here. Usually you can have also another class on top, which is called the class PP. So in this usual notion of all these things usually mind certain thing in the probability. So essentially one can see that all these probabilities, all these p's will mean a polynomial, and then all these initials means a certain thing about what we expect this polynomial to be. Okay. So let's start with the more, before I started, let's just make a reminder. So maybe I put examples which are not decisions problems. Usually in complexity theory, we use center on complexity classes related to decision problems. So this means we are interested in languages. So when I mean a language, I mean use a subset of, imagine, this is just the alphabet. So it's just a subset of words with zeros and ones, which encodes something, and essentially the main problem that one tries to solve is if X belongs to L. And this is what they're called decision problems. So you really care if some certain kind of object or word satisfies a certain property. So it's always yes, no questions. This is not about really necessarily computing with actual numbers. So many times these classes will restrict to these decision problems. So, okay, so when we start computing with randomness, the main idea is, so usually an algorithm is you do a step, a deterministic algorithm, you do a step, and then you know always which is the next step, depending on the input. So I will not use the formulation with Turing machines, and I will keep informal, just for simplicity. So we have an algorithm, deterministic, is that each step determines the next. So this is the basic idea of an algorithm, a deterministic algorithm. I assume here everybody knows what is an algorithm. So a probabilistic algorithm is essentially this similar idea, but now we can have several possibilities, and essentially you throw a coin or you use some random number generator to decide which step to take. So essentially is from each step, the next step is chosen at random. From a family of possible steps. So this is the main idea that differentiates a deterministic algorithm from a probabilistic algorithm. So the first, in way of using these algorithms, there are certain strategies that you can use for gambling, because you want to arrive to the answer. But of course, using probability, it means that you can allow certain errors to happen. And so the idea is, okay, which kind of errors I can allow myself to risk in order to get to the answer. So we get more power because we don't have to be so picky about writing every step and determining everything, but many times it's at the cost of being wrong or not knowing how much time the algorithm will take. So it depends a lot on the choices that we make. So the strategy 1, for example, we will use that I am happy if the probability of having the right answer is bigger than 1/2. This will be like the first thing that one will say, okay, if I have more than 1/2, I'm happy. The problem of this kind of algorithms, usually when you have this street inequality, is that, okay, one way of really incrementing the probability of an algorithm, this is really tricky, is you repeat the algorithm several times, and you look at the majority of the answers is a yes, then I output a yes. If the majority of the answers is a no, then I output a no, and technically this probability will go up. But the problem here is that this tight is really not really tight. So repeating the iteration once and again and again and again will really not give me a way of solving this. So then I can do, this is strategy 1, and this is essentially what is the class PP. Then I can do in strategy 2. So the thing is, strategy 2 is, okay, this thing was that is not good enough for me, because I really cannot repeat, I cannot really estimate how right it will be. So then the idea is asking something more. So I am happy if the probability of being right. So now I ask for a 2/3 of the time. And this is what is called PPP. So essentially the difference of this is what is called probabilistic polynomial, and this is bounded probabilistic polynomial. Because in this case, usually you can use the equality here. In this case, you really have a good bound on the probability of being right. So you know that 2/3 of the time you will be right, but this have certain big consequences of the algorithm, because essentially there is something called error reduction.
So instead of 2/3, you can say 1/2 plus epsilon. Right.
Yes, but you can even say less. Because the thing is, there is a procedure that is called error reduction, which is the idea, okay, I run one time my algorithm, let's run it several consecutive times, and now I take the majority of the answers. If it is a yes, then I say yes. If it is a no, then I say no. So this will be the idea of this. So the error reduction is just apply your algorithm several consecutive times and pick the majority of the answers that you got. So in the error reduction, the good thing that we have is that if the probability of being right, if we even ask a lot less than this, so if we just ask that this is 1/2 plus this is length of the input, so if there is some constant so that my probability is used a little bit more of x, and this depends on the length. So the longer my input is, the less right it will be. Then you can really force that the probability of being right, this is really is just 1 minus 2 and then minus x to the t. So yeah. So essentially you can force for being slightly above 1/2, with something that really this, the bigger the input is, this will go nearer 1/2. You can really force that you can obtain an algorithm that essentially will tell you that you are exponentially near of 1. And the longer is your input, then you are even nearer of 1. So this is a really important property of why the class BPP is really considered more effective than PP. Because essentially in the class ZPP, you can really get a really high probability near 1 of being certain that the answer is correct. But in PP, a priori, there is almost no way of getting above this 1/2 because you don't have this plus this small thing. And this is, if you can see, this is better than epsilon because the bigger the input, this will go smaller and smaller. So it means like, yeah. So this is like the strategy 2, PPP. And now there are the RP and co-RP. So the strategy is, this is strategy 3, is similar to BPP, but now you ask not only that you want to have a certain probability, you want that in one of the cases you are always sure that the answer is correct. So the strategy 3 will be, so I am happy if the probability of being right is bigger than 2/3, and here we have two things. So the first thing, this is always a little bit difficult to remember. So if the output is x doesn't belong, if the output is x belongs to L, I know it's right. And the other possibility is if the output is the same thing. This class here, so this class here is essentially what is RP. And this class here is essentially what is co-RP. That will really later see examples of these two things. So this is how you can handle. This is the strategy 1, strategy 2, strategy 3. So you essentially first, you can ask bigger than 1/2. Then we can even be a little more strict. I really want to have a bounded probability. Then by a certain reduction procedure, this is enough to guarantee that the probability will be really near 1. So this is really something really good that you can ask for a probabilistic algorithm. And the strategy 3 is even more. You ask that if you have a certain kind of output, you know that the answer is right. And now we go to the fourth strategy. So all these strategies in some ways outputting if the answer is right and the answer is wrong, but you more or less know that in all these cases the time is polynomial. So you are just gambling for how sure is the answer. The fourth strategy is which is essentially what is represented by this ZPP, and this is the strategy 4, is I really want the answer to be sure, but what I will do is I will gamble with my time. So essentially is the answer always is right, but the time is just expected polynomial. So this is the essential property. You know that the expected time is polynomial. Maybe when you run, it can run, you don't know how much. But you know that more or less the expectation of this time will be a polynomial in the size of the input. So this is essentially the class ZPP. So I will note, so now before starting with certain examples, the only important thing to remember is that here, like in complexity theory, usually the big thing is you know a lot of definitions. You almost never know which classes are equal. So essentially, it is known now if this is equal, if this is equal, or if this is equal, or if this is equal, or if this is equal. Or if this is equal, so essentially you don't know any of the part of the tower if it makes sense to define it or not. So one of the few theorems that is known about the relationship is that if you have the RP intersection with co-RP, so if you know that you have an algorithm that belongs here and belongs here, then you will know is that you can design an algorithm in this form. So essentially the main idea is you run your algorithm in RP. If there is a certain answer, you know that the algorithm, the element belongs to the language. If it is no, then you run the other algorithm. If here it says no, then you are done. But if here says yes, then there can be some probability. Then you run again the other algorithm, and you do this sequentially doing it. And then you will get an algorithm that in polynomial time it will end, because by probability one, it belongs to the language or not, and one of the algorithms will output this with sufficient time. But it necessarily can run infinitely forever, this algorithm, if you are really unlucky. And then the ZPP, the idea for going here or here is use cut it at some moment the computation. And then you just say, okay, if you cut out and you didn't have an answer before this time, you always say yes or you always say no. And then it will give you an algorithm to put the problem here or here. So this is another way. So if you have an algorithm of this kind and you are not really patient, you can always stop your machine at some moment and be like, I'm done. If this is not answer, I say yes or no. Okay, so by now this is the only relationship that is known about the classes that I write in here. So now let's put a few examples of how one can use probability to obtain nicer algorithms. So because the nice thing of probability is that it makes many algorithms a lot simpler. And this is what we saw now. So the first thing will be an algorithm to find gate elements. So essentially, this algorithm has a certain gate and a certain sequence of numbers, x. And essentially what this algorithm will do is it will output to you the k element. Okay? So the way that this algorithm works is choose I at random. If the let's say j such that xa is less than x less or equal than xk is equal to carry, we are done. Otherwise, if this number, up here, let's call this number, if this number is strictly less than k, then do k by element. So you do k minus this number, let's call this number L. So if this number, then we do k minus L and x getting the xj such that xj less than xk. And if L is bigger than k, so do find the element in the same k and the same x, but now keeping the ones that are above, because I don't really care about this. Okay, so the main idea of this algorithm is you want to find the element that is in the k position. So you essentially choose an element of your family of numbers at random. Then you look the elements that are below this element. If there are exactly k minus 1 elements, then you know that this is the kth element of your sequence of numbers. If not, it means that, this number was below, and in this case I will just drop the ones that are below it and this number, and then I use k minus, so I just find the k minus L that will be the kth of the set, so I will just drop part of the set. And if this is after the kth element, then I will keep this element and all the rest, and then I will obtain a smaller sequence of numbers where to choose the kth element. Yeah?
So is X an infinite sequence? And if so, how do you choose the
This is computationally. I mean, X is always a finite sequence. I mean, you never choose when you compute this kind of things infinite input. The X is a finite sequence, but of course, when you are in real world, finite things you really have to do in an efficient way. And this is, for example, a really easy way of choosing the kth element. You just look at random. If it is not, then you drop certain elements, or the one above or the one below, and then you reapply your procedure. And at some moment you will find the element that is in the kth position. I mean, this algorithm, for example, is not an algorithm that falls in this category because it's not a decision language. This algorithm really outputs which is the element in the kth position. But the important thing of this algorithm is that even though it is probabilistic, you can really give a nice bound on the time that it runs that does not depend on the expectation that is polynomial, and the answer will always be right. What you will have is that the expected time of this algorithm will be lower than the maximum worst case time. So it's an algorithm, yeah, in general it will be good or bad, but it's a good method of doing. A variant of this algorithm can be used for sorting, where you essentially do the same strategy. So essentially you want to sort a sequence of numbers. So what you do is you pick an element at random, then you divide the set between elements that are bigger, elements that are smaller, and then you apply again the algorithm for each one of the subsets. And then you do this iteratively. This algorithm, for example, this one in which you do again this divide and conquer strategy. But the thing, instead of looking for a good element, you just do it at random. And for example, in this one of sorting, you will have that the expected time will be n log n in the size of the input, while the worst time will be n squared. So you know, okay, there is a polynomial bound, but you know that more or less it will be linear, respectively, if you are not really unlucky. And then, let's put two of the big examples of problems that were in these two classes. So one of these is what is called the polynomial identity testing. So I give you a formula, and the big problem that you always have with the formula is that, yeah, for example, I can give you okay, so something like that, or something more complicated, and now I say to you, this is the zero polynomial or not. Of course, this is some problem that here is easy to solve because you can always expand the formula. But in general, you have the problem that, yeah, expanding the formula can require exponentially many monomials to look at. So what you do instead of this is, the algorithm for solving this is pick a random tuple, a random numbers. Evaluate, if the evaluation equals 0, output is 0, and if the evaluation is different than 0, output different than 0. Essentially, this algorithm, I mean, a priori one has to prove, but the one thing is, there is what is called the Schwarz-Zippel lemma that will guarantee you that if the formula represents a non-zero polynomial, then you know that with high probability, a random tuple of numbers will evaluate in non-zero. So essentially, this algorithm, you know that if you get a 0 in the evaluation, you know with high probability that this will be the zero polynomial. And if you know that this is non-zero, then you actually know that the polynomial is non-zero, because it's impossible that something that is 0, when you evaluate on something, gives you something that is non-zero. So this is one of these big problems that is here. My model does not fail, this problem is in this class. Because no, it's in Core B. And This is one of these problems. Another problem that was in the same class was this primality testing. So one of the very famous algorithms for it was probabilistic algorithm. So you were just checking if the main idea of this algorithm was if a number is prime and you have that the square of a number is modulo this number is 1, then you know that this number is or 1 or minus 1. So the idea was applying this successively. So you take the number of elevated to the power. If this is, since this is 1, then its square root has to be minus 1. If the exponent is still even and this is 1, then you go one exponent less and then you do this. And then again you check. But the problem of that algorithm, what happens is that then by the AK's algorithm that I will not explain, essentially they show that this language that usually is called like this prime belongs to P. So essentially they show that the probabilistic method does not give you extra velocity. And now let's come to, because I have to speak about this. And of course one would expect that as there is conjecture P versus NP, all these complexity classes will be different to each other. And now the main problem and difficulty with this with respect to other things is that more or less all the problems that there has been falling, except for example this problem here. It is what is called PIT. This still is not known, so one of the big open problems is if this is solvable in polynomial time. But then one of the big conjectures there is, which essentially is based on a lot of work about these probabilistic classes, and which is one probably of the weirdest conjectures in complexity theory, is you saying if this guy is just equal to this. So essentially what this conjecture was saying is that using probability will, for example, will not be enough to solve if P is different from NP. You will not be able to solve it. Indeed, will not get an NP problem to the polynomial class. So this is really saying that probability may be used to get a lower degree polynomial time, because this is usually what happens with probabilistic algorithms. So instead of maybe getting n to the 7, maybe you get n to the square, which is better in order to execute in a computer. But what you want to do is taking something, if this conjecture is true, something that is exponential to something that is polynomial. So the only thing that probability will really help you is get from polynomial of certain degree to polynomial of a smaller degree, which is useful in practice, but it means that it will not really help you with bigger gaps. So this conjecture is not as bad. It doesn't mean that probability is useless. It just means that probability is useless in order to pass from something that is non-polynomial to something that is polynomial. So, and I will end with this, that essentially is the big question in which if this sequence will be useful in some time in the future, or if it will be used like these things that are used, forgotten at some moment in the future. So that is all.
Thanks.